Hey everybody, Mr. Bennett back with another set of notes. So this is section 5. Again, remember this is the knowledge level. We're skimming the surface, so really you got to dive into this on your own through some of the work that we're doing, the labs that we're doing and discussing in class. But we're going to talk about acceleration really quick, okay? Up until this point, in all of my prior videos, we have calculated constant speed. So we've talked about instantaneous speed, we've talked about average speed, we've looked at how to find that speed, but we've assumed it's constant the entire time. But we know that speed isn't constant. Objects rarely reach a constant speed without some kind of acceleration. So constant speed is not impossible, right? I can get on the highway and I can hit cruise control and stick at 70 miles an hour or whatever. But I have to accelerate up until that point. I can't just jump to 70 miles an hour. There has to be some kind of time where I lead up to that. This is the equation for acceleration. This is looking at a change in velocity. So we are doing VI stands for initial velocity, or this is the starting. This is how fast you are going at the start of your measurement. VF is the final velocity. So how fast am I going when I'm finished versus when I start? The change in that over a set amount of time is the acceleration, which is A. So you can label that up. We're going to come back to final unit in a moment because I want to make sure you have some context for that idea. Acceleration, if we were to give it a definition, is the rate of change in velocity. Okay, so we've turned this equation now into a quick definition. Acceleration is the rate of change, how quickly do we change our velocities over a given amount of time. Okay, so we're going to look at one example here. We're going to leave it at one for now because we're going to do a lot of this in class. A biker begins to move from an initial speed of 0.0 meters per second, so this is your V initial, to a final speed of 25 meters per second. So this is V final, and the time it takes to do that is 10 seconds. Remember, if we carry down our equation, so A acceleration equals VF minus VI, put this all over a time, and we can fill in our variables. Remember, this is knowledge level, okay? The application comes later, so just grab your data, mark up your question, and grab your information. So V final is 25 meters per second, and we subtract 0 meters per second from that, and we divide the whole thing by 10 seconds. And what we do is we need to simplify. We have like terms up top, so this becomes 25 meters per second all over 10 seconds, and then we divide. Now, meters per second as a unit whole is not the same as seconds, so this is 25 divided by 10, so that gives you 2.5, and if we rewrite this, meters per second, and what this really means is here's a velocity, right? This is a speed. So 2.5 meters per second, we are increasing by that much every single second. The other way you're going to see this written is we combine our seconds in the bottom. So we end up with 2.5 meters per second squared. These two statements mean the same thing. 2.5 meters every your velocity, 2.5 meters per second for every second you watch this object. So your final units, if we go back up to the top, right, this is going to be a distance over time squared. So you can see this a couple different ways. You can do meters over seconds per second, meters per second velocity for every second. In this, you're not going to see this too often. The way you're probably going to see it is in meters per second squared, or distance over time squared. Remember, the total units don't matter. And that's where we're going to leave this for now. There's some extension we're going to do in class. We've got a lab. There's all kinds of things. I'm going to come back and do speed versus time in a second follow-up video. So consider this part 1. Part 2 will be posted. So you need to come back and make sure you take a look at this one. And when you do, I'll see you then.